thank you very much for coming to Ringing Maximum Performance from vSphere for extremely demanding workloads and customers. Presumably you are the extremely demanding customers. So, I am Josh Simons. I work in the office of the CTO, Chief Technologist for High Performance Computing, and I'm joined today by my colleague Na Zhang, who also works on high performance computing. So, what we do is, as I said, we focus on high performance computing. We perform various kinds of performance experiments, looking at things like high-speed interconnect, low latency, proofs of concept with customers. We work with the R&D organization to, when we find problems that affect the kinds of workloads that we're interested in, we work with R&D to get improvements put into the platform. And today what we'd like to do is share with you some of the learnings that we've had in looking at a couple of different application areas, try to give you some guidance about how we've report to you what kind of performance we're able to achieve, and then what sort of tuning we applied to get that performance that we're showing you. Okay, so the three areas that we want to talk about are high performance computing, and we'll define our terms there in a minute, and we'll give you an example of an engagement that Na was involved in with financial services. And then I'll spend a little bit of time talking about enabling compute accelerators in vSphere. And then we'll finish up with one other topic that's actually not on the agenda. Okay, so first up, let's talk about high-performance computing. So first off, what is it? High-performance computing, generally speaking, tends to be technical workloads. These are engineering, research, and scientific workloads. They're often very parallel. They're extremely compute intensive. They tend to be high scale, although not always, and they're also very data intensive. If you look here on the right-hand side, you can see various areas where these kinds of workloads appear. It turns out a pretty large percentage of the VMware customer base has these sorts of workloads running in their environment. It's often not the case that it's running virtualized. It's usually running bare metal. So we spend a lot of time looking at performance in this area to help you and also to help HPC people understand both the value of moving into a virtualized environment and what kind of performance you can expect if you do that. There are two different kinds of application types that show up in this space. There are throughput applications, which all of these run on a cluster, which is what you're seeing in the middle there. The throughput applications are large numbers of single process applications that are run in parallel on top of that cluster. The MPI, or message passing interface applications, are more complicated and more difficult for us to virtualize. These are pieces that run spread out across the cluster, but that do a lot of very intense intercommunication between them. So things like communication latencies become extremely important. So that's what HPC is. And before I get into details about the performance and tuning, I did want to mention that yesterday we announced that we have a new vSphere edition called vSphere Scale-Out that is specifically targeted at HPC workloads and big data workloads. Big data in this particular case means Hadoop and Spark. It's a new edition. We've removed a few features. We've sort of customized it to what we believe is most important for HPC and for big data. And perhaps most importantly, from your perspective, is that it has a very different price point. You can ask for details about that when we get to the Q&A session if you like, but this is exclusively targeted at those workloads. So it's not for hosts where you would be mixing workloads. You can only use these SKUs for running these particular workloads. Okay, so before I talk about performance, let me just give you a quick sketch of why we have customers that are now moving their HPC workloads and environments into the VMware infrastructure. So none of this is rocket science. This is all really basic stuff to everybody in the room. But if you think about it from the perspective of an HPC environment where they don't know about virtualization and they're running on bare metal, then this is news to them in many cases, right? So this idea that in a bare metal environment, when they create a cluster, they run a single operating system instance version across that entire cluster. There's no flexibility in terms of choice. So obviously, when you introduce VMs, you have the ability to bring whatever software stack you want very dynamically onto that infrastructure, right? So mixing Windows and various distros of Linux, for example, obviously very, very easy to do in a virtual environment. Also, the fact that you have the VM abstraction, as we know, it gives you both security separation. So if you put user A's workloads and user B workload in different VMs, then you have separation from a security and from a fault perspective. Again, in the HPC bare metal environments, everyone's jobs are intermixed into Linux instances, and so a failure of one process could potentially affect other users. So we avoid that by virtualizing. Scientific reproducibility, I won't talk about that. We do have customers that are quite interested in it. The fault resiliency and dynamic load balancing, the use of vMotion and/or DRS, it gives us the ability to dynamically move workload around. It's not possible to do that in these bare metal HPC environments. The fault resiliency is particularly interesting because they often have jobs that are very long running, and they don't have checkpointing built into these jobs. So if you're running one of those, say it's been running for a week on a machine, and we see a fan failure or some correctable soft memory error rates increasing, we can actually just vMotion that workload off to another machine and not lose that week's worth of work. So it's something we can do to drive up the overall utilization of the infrastructure. Okay, so let's talk a little bit about performance. So again, the throughput workloads, lots of independent single process jobs that may or may not be multi-threaded. You can see some examples here of those kinds of workloads. Very popular financial risk analysis, for example. Lots of Monte Carlo simulations that are run across very, very large clusters would be one example. So the task here, our performance comparison, is an apples-to-apples comparison. We run on an application, bare metal, then we use the same exact Linux instance, the same application, and then we evaluate how close we can get in terms of performance. So this is just a sort of representative example of what we can do with this class of application. So the way to read these charts, they all look this way, is that we're showing you performance ratios on the y-axis. So higher is better. 1.0 means that we're delivering the same performance in virtual as you get in bare metal. And this happens to be a life sciences benchmark. And you can see the different elements of that benchmark. They stress different aspects of the system. But what you see here pretty much across the board is that we're delivering 98, 99% of bare metal performance for these applications. And you'll also note that this was done on ESX 5.5, which is pretty ancient at this point. But given the numbers, we really haven't felt the need to rerun these on the later version on ESX 6.5. So, and I guess I should say, I'll mention this again, this is a representative sample. We've done other sorts of testing. By and large, for these throughput applications, you will get very, very close to bare metal. Certainly under 5% degradation, but usually much, much closer than 5%. So how do we do that? It turns out that you really don't need to do all that much tuning. So at the BIOS level, we usually use OS controlled for power management, and then we set it at the ESX level. You can see that the logical processors and the hyperthreading is something that we'll come back to. So normally you would turn hyperthreading on in your enterprise environments. In an HPC environment, bare metal environment, they usually don't turn hyperthreading on. So this is a different sort of thing, and we'll come back to this in a minute. Turbo boost on and memory interleaving off, because we really want to take advantage of NUMA capabilities on the system. Okay, so at the vSphere level, we usually go with balanced power management for these applications, unless they're really, really latency sensitive. If they're latency sensitive, then you would want to go with sort of a maximum or performance setting for the power management. Virtual NUMA is really important, especially if you're dealing with a VM that is big enough to span physical sockets in the box. You want to make sure that the NUMA topology, that physical NUMA topology that sits underneath that VM is reflected up into the VM so that the guest operating system will see the correct NUMA topology. Because if it doesn't, then when, for example, Linux starts to make its own NUMA optimizations, it will start making bad decisions and you'll get bad performance. So it turns out in earlier versions of ESX, you needed to set cores per socket to get that to happen. But with ESX 6.5, we do that automatically. Generally speaking, newer versions of Linux, and for those that don't know, most of HPC is Linux-based, so we focus for the most part on Linux. Newer versions of Linux tend to get better performance. And now in terms of the proper sizing of the VMs, so one vCPU per physical core. So remember I said turn on hyperthreading, but don't map your vCPUs to hyperthreads. That's not usually a good idea for HPC due to the nature of the applications. They tend to be pretty cache friendly and you don't get an HT benefit. But by turning on HD at the BIOS level, it actually gives ESX a little bit of breathing room and some threads that it can run on. So, and we've seen that that actually does offer some improvement. Okay, and it's also not necessary to leave some CPUs or some cores for ESX. We understand that typically HPC people, when they buy a 20-core system, they want to run 20 cores worth of workload. So all of the testing, most of the testing that we do runs that way. So the performance results that we've showed you are assuming that you're using all the VCP, all the cores for workload. And as I mentioned earlier, if you do have latency-sensitive workloads, then this white paper that's mentioned here would be quite interesting, and also the power management would change. Okay, so now let's talk about the MPI workloads. These are, as I said, more difficult to virtualize because they are so communication intensive. Okay, and for those not familiar with HPC, let's just be very clear about what it means to run an MPI job on a cluster. So here we're looking at a 16-node cluster. We're running a single 20 vCPU VM on each of them. These are 20-core machines. And when you run an MPI job across all of that, you basically crank up 320 processes on your Linux instances, and they all intercommunicate. So there's intercommunication happening between the red dots within a box, and a lot of intercommunication happening between those red dots on different boxes. And how much actually happens depends completely on the algorithm that's being run for solving the problem. Okay, so let's talk about sort of figure of merit here. What really matters to get these applications to run well is delivering low latency performance. And in HPC, it's typically the case that customers use low latency, special purpose low latency interconnect. So InfiniBand is a very popular interconnect there. We use InfiniBand from Mellanox Technologies. So the test setup here is 2 different hosts. We're running ESX, and then we run one VM on each host. We have an InfiniBand card in each host, and the idea is how fast can we ping pong messages back and forth between these 2 hosts, because that's what's going to be the gating factor for delivering good performance. Okay, so one other little tidbit before we move on. On the left-hand side, this is how they achieve ultra-low latencies in a bare metal environment in HPC. So these devices, like InfiniBand, actually allow you to do user-level access directly to that hardware. So it's called OS bypass because you are stepping around the operating system. And so from the application's user space itself, you can talk directly to the hardware and send a message and receive a message. So on the right-hand side, the virtual version, we do essentially the same thing. So we have the guest kernel and we have VM kernel in our case. And again, using VM Direct Path IO or pass-through mode, you can pass that InfiniBand device up into the guest operating system and then use the same trick to get low latency and high performance. So if we do that, let's see what we can do. And this is sort of a historical perspective. What we're looking at on the x-axis are the message sizes. So these applications that I'm talking about, they can exchange very different sized messages. Some of them are extremely latency sensitive, and they might exchange millions or even billions of single byte messages. But many others exchange messages that are larger. We focus on the small messages because this is where latency matters the most. So we're going to look at that range of message sizes, and then we're going to look at half round-trip latency, which is the figure of merit for HPC. How fast can I move it from this box to this box, or really from this process to this process? Okay, so bare metal InfiniBand for the generation that we're looking at is about a microsecond to move a message from one process on one box to another process on the other box. So if you looked at ESX 5.5, you see that we're about 2 microseconds, and we have this strange anomalous bump here. So 2 microseconds sounds good, but that's 100% overhead. So that doesn't mean that all MPI applications run with 100% overhead, but it does mean that a lot of them are impacted by this overhead. So not so good. With ESX 6.0, we had about a 15% performance improvement. We still have the strange bump. You go to 6.0 Update 1, which you think would maybe not do all that much because it's an update release, and we go here. So now we're about 15% away from bare metal performance with 6.0 Update 1. And then with 6.5, I bet you know where I'm going. It goes to there. So I now need to say the opposite. Just because we've removed this latency overhead doesn't mean that all your MPI applications run at full speed, but a lot more of them get a lot closer to full speed. So let me show you some numbers for that. So Again, we're looking at performance ratios, higher is better. And now we're looking at, it's not a suite of applications. These are just a pretty broad range of different kinds of MPI applications that are popular in high-performance computing. We're running 320 MPI processes in this case, as I showed you in that earlier diagram. And so we have fluid dynamics codes here, weather codes. What else do we have? Molecular dynamics codes as well. And you can see it's a broader range of performance, right? So some of these are up in the high 90% areas. Some of them are in the sort of 80 to 85%. I want to be very clear to say that we're not claiming that we can run all of your MPI applications even necessarily at this level. I can find applications that will have bigger degradations, which is why it's really important if you're interested in pursuing this approach that you do some kind of a proof of concept to look at the particular applications and models that you care about to make sure that you can get good performance. Now, having said that, we'll show you what we've done to achieve this level of performance, and we also continue within the group to look at ways that we can perhaps mitigate some of these other overheads that are causing these issues. But we're relatively happy with where we are right now. So what's the tuning? So the BIOS, everything's the same as what I said before, nothing different. On the power management, we've set that to maximum, and that's because of the latency sensitivity of these applications. So that's really important. For InfiniBand, as I mentioned earlier, you would use that in direct path I/O mode or pass-through mode, and we show you there how to configure that if you haven't done that before. The virtual NUMA, again, is also critically important. Typically with these MPI applications, you are running large VMs. You tend to not run lots of smaller ones, so you're going to have a wide VM, and you do need to be careful to make sure that the vNUMA topology matches the underlying topology. And again, same for the vCPUs, 1 per core, not 1 per thread. And the only other thing that's different is that because you're using a pass-through device, you need to reserve memory for the VM. That's a given. That's not a performance thing. You just can't use the pass-through device unless you actually do that. And again, same white paper for dealing with the low latency. There are some additional tunings you can do. For example, if you have NFS traffic that is latency sensitive. Okay, so if that level of tuning doesn't help you, I mean, it doesn't get you where you want to go, there are a few other, maybe somewhat more exotic things that you can do. Maybe they're not exotic, but they're a little bit more. So you can reserve CPUs. Okay, so the question is, how much CPU can you actually reserve? So one way of figuring this out would be to get onto your ESX system and issue this command. You'll see a bunch of output, but you will see a line that has host in it. So here, it looks like this. And what you see on the right-hand side are the number of megahertz reserved by ESX, essentially. So, okay, so let me work through this. So how do you calculate that? So it's basically the reserved CPU amount is the number of PCPUs in your box minus the reserve memory divided by the host, the number of megahertz you have in your processor, and then multiplied by the megahertz of the, or the gigahertz, megahertz of the processor. So let's work through an example. So for a 20 CPU systems that we've been talking about, we've got 20. We've got the 5914 from the line above. We're using a 2.6 gigahertz processor. And so then the math would be that's 2.27. Ceiling means round up, so 2.27 rounds up to 3. So we've got essentially 17 CPUs worth of megahertz that we can use for the workload. So you're reserving 3 for ESX. And you can also turn on latency sensitivity. This was a new feature that we added as of ESX 5.5. You can see some of the optimizations that it does here. We tend to not use this unless you really need it. It's somewhat of a heavy hammer, but it will potentially give you some performance improvements. Now, if you apply both of these, in the testing that we've done, we've seen about an additional 8%. So not a huge amount of performance increase, but it will give you a bit more. Okay, so now I'm going to turn it over to Na to talk about her experiences with financial services.
Thanks, Josh. Okay. Financial services is also another performance extreme case. It's very sensitive to networking latency and bandwidth. Thus, they need special tunings. I will share my experience working on proof of concept to run a financial application on top of vSphere. This financial application is a high-performance market data platform. I cannot tell the name of the application, but it's being used by multiple famous banks to do like a risk analysis or high-frequency trading. So in this proof of concept, we have done the latency test of bare metal versus virtual and try to reduce the overhead in the virtual environment. This diagram shows the minimum setup of this financial application. You can see there are 3 hosts. The first host is for publisher and a subscriber, and the second host is for data collector, and third host is for data distributor. Each host has 2 dedicated Ethernet cards. It's 10 gig Ethernet cards. And the networking between the data collector and the data distributor is multicast based. So this is the typical setup of this financial application. And the latency is defined as the publisher generates the data and the data propagates through the data collector and data distributor and reach the subscriber. So the financial data could be like a stock trading information or quoting information. And the subscriber will receive the data to trigger some financial operations, like put like an order. So you can see it's very latency critical. For example, high frequency trading case, you cannot tolerate much overhead. So in this proof of concept, first we work with a company who designed this financial application to configure 3 host testbed. And we apply the tunings they want, and we get the good bare metal results as they expect. Then we converted the environment to virtual, and we compare the performance. Before I'm showing the tunings and the optimization, the results, let's see the earlier proof of concept results. This was done in ESX 5.5, and this figure shows the latency. The y-axis is latency in microsecond, and lower is better. The x-axis is the number of updated messages per microsecond. The lower curve is bare metal, and the upper curve is virtual. So you can see the performance results was not very good. It's pretty bad. And especially the bare metal range was around like 100 microseconds, but the virtual range was around 280 up to 400 microseconds. And there was some like bumps or spikes, which was undesirable. So based on these earlier proof of concept results, we have done a new proof of concept. In this new proof of concept, as first step, we configure the 3 host testbed and apply the customer-specified tunings. Since this is a financial application, they have multiple complicated tunings. For example, in the server BIOS, it requires to use maximum performance profile and disable any power saving features. And at the OS level, first is a Linux environment. So it needs to disable any unnecessary system services. Also need to configure like a kernel parameters and the server adapter parameters. The kernel parameter configuration and the kernel server adapter configuration are both for the networking tunings. And one important thing is they need to pin the application to a particular socket or NUMA node. And that node, we should have the Ethernet card attached to. Also, it will have higher latency performance. For example, there are some tools in the Linux, you can identify your system topology, like LS topo. So you can see where the Ethernet card attached to, and you pin your application to that particular socket. That will more close to Ethernet card, so you can get higher latency. Other than the socket level, furthermore, they also need to pin the application threads to physical cores level. For example, the subscriber thread and the publisher thread. For example, they need to pin the subscriber thread to physical core 0 and subscriber thread to physical core 1 and pin other services to other cores. Finally, also need to apply some application level tunings to achieve the maximum performance according to the deployment scale. So you can see for this financial application, it has very complicated tunings and very specified tunings in order to get the maximum performance. So we have done that in the 3-host testbed, and we achieved the results they want, and we convert the environment to virtual. So in the virtual tunings, first, in the BIOS, we use the same setup, maximum performance profile, and disable any power saving features. As for vSphere, one important thing is for the Ethernet card configuration, we use pass-through mode. Josh already mentioned the advantages and the disadvantages using pass-through mode. So the advantage is you can get maximum performance, but the disadvantage is you cannot enable some vSphere features like vMotion or taking snapshots. But since this is a pretty performance critical case, it's not necessary to enable vMotion. So we recommend pass-through mode, or called direct path I/O, for achieving maximum performance. And second, since they requires to ping application threads to particular physical cores, so in the vSphere, there are two settings we need to set in order to guarantee that. The first setting is we need to set node affinity. So we can force the VM to be allocated on the socket where the Ethernet card attached to. So assuming we already figure out which the socket the Ethernet card attached to using the Linux tool. So for example, it's socket 0. So we can use NUMA.nodeAffinity equals to 0 to force the VM to be allocated on socket 0. And the second, like MPI, we can set latency sensitivity to high and reserve CPU. That will guarantee you can have inclusive access of the CPU to the pCPU. So when you do the application level pinning, you pin the application threads to a particular vCPU. That vCPU will map to a particular pCPU. So you can have a dedicated CPU resources. And also, we recommend to publicize VM. In this case, it's not very good to create a very large VM because that will lead to actual maintenance overheads. So just make sure your VM could be fit into one NUMA node. And finally, needs to replicate all the OS level tunings as a bare metal in the guest OS. For example, like a server adapter tunings and the kernel configuration tunings in the Linux guest OS. So that's all the virtual tunings we have done in the newer proof of concept. This is the new results. So you can see now the virtual performance is much closer to the bare metal. And this is quite good. And the customer was pretty satisfied with these newer results. So I think there are two takeaways from this part. First, even like a financial services application, this quite demanding application, with proper tunings, we can still achieve very good performance results. And the second thing is, the newer proof of concept was done in ESX 6.0 update 2, and the old results, the bad results, was done in ESX 5.5. So that speaks to the newer version high performance improvements. So we always recommend you to upgrade your ESX to the latest version because we also expect the 6.5 will have better results than these results. Okay, thank you. And next, Josh will talk about compute accelerator use cases. Yeah.
It would be better to wait if it's okay. Yeah. Thanks, Noah. Okay, so compute accelerators. These are becoming they've been important for a long time in high performance computing, but we are seeing them emerging in a really, really big way in machine learning, for example, especially deep learning. And so I want to talk a little bit about, so it's not just GPUs. So that is the most popular way of doing compute acceleration, using a GPU in a compute mode, which is called GPGPU. But there are also FPGAs that are being used for this. And Intel has the Intel Xeon Phi family of products that also give you a very large amount of CPU power. So I wanted to talk a little bit about how to enable these devices in vSphere, because for whatever reason, our documentation sort of cleverly doesn't help you do this. If you follow our documentation, it will fail. And we've had direct conversations with a fair number of customers helping them to actually enable this. So for example, to be concrete, the NVIDIA K80, or multiple K80s if you like, or the NVIDIA P100, these are high-end NVIDIA GPU cards, they can be used in pass-through mode with ESX. And we can help you do that if you're having trouble with that. So I'm going to show you how to enable it on ESX 6.5 Update 1. As you go back to earlier versions of ESX, there are more and more problems, I would say. It becomes more difficult, but if you're not using ESX 6.5 or 6.5 Update 1 and you want to enable one of these devices, please contact us and we will help you do it. It's not hard, it's just that you need to know the magic, and let me show you some of that. So before I show you that though, let me give you a sense of what you can get when you do this. So here we're looking at the Shock benchmark, which is a pretty common computing benchmark that uses GPU. Again, we're looking at performance ratios, and it's a pretty comprehensive benchmark. It looks at a lot of different aspects of compute. And you can see across the board, except for maybe a tiny dip on the right-hand side, that you get essentially identical performance, bare metal versus virtual. So you get all the performance, but you just need to know how to do this. So let's talk about this. So the trick is here that these high-end devices have what we call large bars. So a bar is a base address register. It's the amount, think of it, it's the amount of memory that PCI device maps so that it can interact with the host. So large bar devices use more than 16 gigabytes of mapping. And that large size causes us to have to do a few additional things in order to get this working. Some examples of large devices are listed there for your reference. Okay, so one way of figuring out whether or not you have, and probably, you could go look at the spec sheets online for the vendor, or here's something you can do using ESX to figure out whether or not you have a large PCI bar, a device. So if you try to boot your virtual machine with that device installed, you will see lines like this. So we're looking at device 9 here, right? So there are 3 lines, one for each of the bars that this device maps. And then over here on the right-hand side, you see some decimal values. Sometimes it's not clear that they're decimal, but they are. If you add all of those numbers up and they add up to more than 16 gigabytes, then you're dealing with a large bar device. And then the advice that we're giving here makes sense, is relevant. Okay, so the first thing you need to do is in your BIOS, there is going to be some kind of a setting that is usually in the PCI section that says something about 4 gigabytes. 4 gigabytes decoding or mapping above 4 gigabytes, something like that. That option in your BIOS needs to be turned on. That depends on the vendor for its exact wording. You need to use an EFI VM, and your OS installation, your guest OS installation, needs to be an EFI installation of the guest. This is so that you can get access to the 64-bit MMIO, which I'm going to talk about right now. So in order to use these large bars, you need 64-bit MMIO, memory mapped I/O turned on. So you turn it on with the first line, and then you need to set the region size for that with the second line. So the way you do that computation is shown on the lines underneath that. So you basically take the number of those high-end pass-through devices that you want to enable inside of that VM, multiply that number by 16, round it up to the next power of 2. So the example there is for 2 devices, you take 2 times 16, you get 32. You round that up to the next power of 2, which is 64, and that's the number that you would specify. So once you've done that, you then just go do pass-through the way you normally would. You set the device at the ESX level as a pass-through device, and then you pass it into the VM the way you normally would, and it will work. It definitely works. And again, more warts as you go back. Contact us directly if you need help with this, with earlier versions of ESX. Okay, so I wanted to mention one other thing. So that's using the device, the graphics device, in pass-through mode as a compute engine. So as I'm sure you're all aware, NVIDIA for a long time has had the vGPU concept, right? That's used for VDI to deliver a graphics experience into virtual machines. Well, they've done something very cool that was announced a couple of weeks ago. They've released version 5.0 of their grid software. And the really nice thing about the version 5 of the grid software is that you can now have vGPUs that are doing either graphics or compute. So you can now carve up a single, say, P100 and run multiple, say, machine learning workloads at the same time on that card. I wanted to show a quick example of some performance that we found when we did a test here. So what I'm doing here, the setup is that I have a single P100 in my machine. I have 2 VMs. Each one of those VMs has half of the GPU passed into it using the vGPU mechanism. So using vGPU. And now I'm running a neural network application, a training, inside of each one of those VMs. I've arranged it so that the one that we're looking at in black is a short-running job, and the one that we're running in red is a longer-running job. So you can see in the first phase on the left, and we're looking at GPU utilization on the y-axis, and then time on the x-axis. So you can see that as they're both running at the same time, the smaller job is getting about 35% of that GPU, and the larger job is getting about 65%. But then something interesting happens. As the lower job starts to tail off and starts to head down towards 0 CPU utilization, you see that the other job very dynamically starts to take more of that GPU, to the point where when the smaller job is finished and not using the GPU at all, you're getting 100% of the GPU used by that other VM, which I think is very nice. It's a nice way of getting 100% usage of the GPU in a very dynamic way. They have also introduced a couple of other scheduling schemes that I'm not going to talk about. They have their use cases. They're interesting as well. I'm sure at the booth they're talking about, at their booth they're talking about them in detail. But I'm quite psyched here because we have 2 different ways of using GPUs now. You can use them in pass-through mode if you need the whole GPU or multiple GPUs, or if you want the sharing capabilities that they've introduced here, then you can go the vGPU route. They also have enterprise-level monitoring, and we have some other really cool features that I think actually were talked about in another session, so I'll mention it. We are working on the ability to vMotion a VM that has a vGPU attached to it. And presumably that would include a VM that is using, say, a CUDA application as well. So this is yet another aspect of delivering extreme performance on the platform. Okay, so the last thing I want to talk about, just really quickly, this is something that Na has been working on, actually. So we've been talking about performance and extreme performance of applications. This is more about increasing your operational efficiency and performance. So she's built this command line tool. We're HPC folks, so we tend to think command line. This accesses the vCenter, using the vCenter APIs, and it will allow you to do a number of different things, but I'm going to focus on one particular piece of this. It's a command line tool that will essentially let you, in one command, create an entire virtual HPC cluster on your infrastructure. And that cluster could, or it could be a machine learning cluster as well, but that cluster would be automatically provisioned and set up. If you were using InfiniBand, it could set up InfiniBand devices in pass-through mode. If you needed to have the high-end GPUs available for machine learning or HPC, you can have that happen as well. And I just wanted to really briefly give you a sense of what it looks like. So the first thing you do is you define what you actually want that command to do by setting up a configuration file. And here we're breaking it up into 3 different sections just to show you. It may be a little bit hard to see. But essentially what you do is you define a set of per VM attributes. So you can see on the left we're setting the memory size of the VMs, the number of CPUs we want the VMs to have, what their data centers are, et cetera. In the middle you can see networking details that we want to provision. And then on the right-hand side we have the PCI information for the devices that we want to set up in pass-through mode. In this particular case, we have an InfiniBand device and a couple of K80 NVIDIA K80 GPUs. So once you've defined all these attributes, you then define, another set of commands that you use for defining the virtual machines that you want to instantiate. And we don't have time to go through the syntax here, but basically you're using the attributes that have been named previously up on the top to, in a very succinct way, define the attributes of the VMs that you like. And so here we're defining an 8-node cluster, or sorry, an 8 VM cluster that we want spun up. Once you've done all that, you simply issue a single command, give it the cluster config that you've just created, and it will go off and do it. So this is something that is not available now. It's something that we're looking at releasing as a fling. I'd be really interested to hear from people if you're interested in this sort of thing, if you'd like to try it. We'd love to hear from you. But we feel like it's a nice way of helping people get these clusters pre-enabled with these high-speed devices in them set up quickly. Okay, so our summary, we've shown you some examples of the work that we've done in high-performance computing and financial services and also around how to enable hardware accelerators, all with an eye towards really enabling access or the ability to run these emerging and very demanding workload types on vSphere. So that, in a nutshell, we have some technical resources for you, various white papers that you can see when you get access to the slides. There are other talks in the Extreme Performance series here in Las Vegas, the hands-on labs that are appropriate. The performance folks, if you are so inclined, would love to hear from you directly about performance around our products. So this is a QR code that you can use for doing the performance survey. And we would also love it if you could take a few minutes to give us some feedback in the talk survey so that we know if we're telling you interesting information and if we've given it to you in an effective way. We'd much appreciate that. Okay, so we're happy to take questions. And if you have questions about the scale-out vSphere edition that I mentioned earlier, Matt Herreras is here. He was instrumental in getting that vSphere edition defined and approved within VMware. So we're happy to take questions. There's a mic here if anyone has questions. Okay, thank you.